Example 13.2 is going to also show us some examples of polynomial functions, just like example 13.1 did, but now we're going to take a graphical perspective. Example 13.1 was the equation perspective on a polynomial. Here's the graphical. All three of these, f, g, and h, each represent a particular degree polynomial. The first picture represents a potential degree 3 polynomial. My middle picture represents a degree 4 polynomial, and my last picture represents a potential degree 5 polynomial. Now, what's interesting about the way to identify these degrees, which is not necessarily something that you're going to need to be able to do just immediately from looking at it, but it is nice to know what to expect when we start getting these higher degree polynomials in terms of their graph, because that is going to be one of the major goals of our study of polynomials, is the ability to be able to graph them with a not the highest level of accuracy possible. We'll reserve some of that accuracy for calculus, but here I want you to notice that on the degree 3 polynomial there are two vertices, or two relative extrema, and the relative extrema are going to split this picture into three behaviors. We have increase, decrease, and increase. Three behaviors, degree 3. Look at your degree 4 picture. We have 1, 2, 3 vertices, and we end up with 1, 2, 3, 4 behaviors. On the degree 5, we have 1, 2, 3, 4 vertices with 1, 2, 3, 4, 5 different behaviors there. Now, this is just the most complex that the degree 5 and the degree 4 and the degree 3 can be. They can end up looking simpler than this. So as the degree of your polynomial goes up, certainly the level of complexity goes up as well, or I should say the potential for the complexity goes up as well. Doesn't always have to. But the other thing that I want you to take away from this is that every single one of these graphs has some similarity. They are all smooth and they are continuous. We are not going to formally define smooth or continuous here. The ideas of smooth and continuous are more formally defined in a calculus course, but we're laying the foundations for that work here today. And we'll start with the word continuous. So the word continuous means essentially without stop. It just continually goes on. Now, from a math perspective, continuity essentially means, can you draw the graph with one fluid pen stroke? Again, this is not the formal definition. This is just a more intuitive approach to continuity. So if I go back and look at my degree 3 polynomial here, I can take my pen and I can graph the entire shape with just one pen stroke. That is the idea of continuity. And that same thing would apply to every single one of these pictures. If I look at G, I can draw that with one continuous pen stroke, and the same thing is true for H. I can draw that entire curve with just one pen stroke. So all these have continuity. Now, not only do they have continuity, they are continuous everywhere. So that's a major factor of these polynomials, that everywhere you look, it is continuous. There is no gaps in the graph. And the other part of this is smoothness. So smoothness has to do with the transitions between the different increasing and decreasing behaviors. So when I go back and I draw the graph for, let's say, the degree 3, if I'm going along my increasing and I transition to my decreasing, it's a very smooth transition. It's not jerky, it's not abrupt. So when we look at the transitions, we can see this very nice, smooth transition, and that is also one of the major features of having a polynomial function. Please be sure to look at example 13.3. Example 13.3 is going to show non-examples, so then you can get an idea of what it means for it to be not smooth and for a graph to be not continuous. But for right now, this should complete what we need to discuss here for example 13.2.